All right, so hi everybody to the Temporal Graph Learning Reading Group. Today we are very happy to have Abigail J. Hayes and Tobias Schumacher from University of Mannheim, who will present what do temporal graph learning models learn. And Abigail Hayes is a PhD student at the Chair for Data Science in the Economic and Social Sciences at University of Mannheim and supervised by Professor Markus Strohmeyer. She previously studied mathematics at the University of Durham, UK, and data science at the University of Mannheim, Germany, having also worked in statistics for the UK Civil Service. The research interests are related to social networks, including temporal graph learning models and realistic synthetic network generation. And we also have Tobias Schumacher, who is a final year PhD candidate supervised by Markus Strohmeyer. He began his doctoral studies at RWTH Aachen University, his alma mater, and followed his supervisor to the University of Mannheim in 2022. Tobias holds his Master of Science degrees in both mathematics and computer science from RWTH Aachen University, and his research focuses on network representation learning, the similarity of neural networks, fairness in rankings, and quantification. And with that, I hand over.
Great, thank you for the introduction and for inviting us to present this work. It's currently published as a preprint, and so there are a few areas where maybe we'll say we're running some further experiments at the moment just to finalize things. But hopefully it's still interesting for you to see. And also we've agreed to do this fairly short notice, so if the slides are not completely polished, that might be a contributing factor. But hopefully everything's clear. If not, don't hesitate to ask clarifying questions. And I will do the first half, and then Tobias will present the second half of the slides. Sorry, it's just come up with a screen. And so the kind of background to the reason why we did this work was originated from looking at the different benchmarks that exist, that I'm sure many of you are familiar with, that have been derived to evaluate the performance of various different models on link prediction tasks with temporal graphs. And when you look at them, there are obviously like differences and similarities between different benchmarks, but there are a few areas that we identified where maybe there's room for further exploration. The title here says weaknesses of benchmarks. I don't know if it's necessarily a huge weakness or just different aspects that could be considered. But firstly, that there's often a focus on the positive edges when we're looking at whether the predictions are correct or not. Where, for instance, the test sets are like 50% positive and 50% negative, but obviously the positive edges actually make up a very small proportion of the possible edges on the network. And for instance, the work by Paul et al. Demonstrated the difference that it makes changing the negative sampling approaches. And so this was an aspect we wanted to consider, is the kind of relationship between positive and negative edges. Additionally, it's unclear what the different models or even an individual model is using to learn and make predictions. They're trained on the networks and then they make the predictions, but we're only then really looking at is an edge predicted or not. And additionally, the tests generally are considering a subset of edges as well. And so maybe some of the patterns of what is being learned or not is being overlooked. And an additional aspect that we noticed was that sometimes heuristics are beating these neural network-based models. For instance, the one mentioned here can sometimes on certain data sets beat some of the models. And so just generally an interest in understanding what these models are learning of the networks was the underlying motivation. And so the idea is to evaluate whether the model can learn specific characteristics by looking at each characteristic in turn and designing a specific data set to train the model on, and then also a specific set of measurements to evaluate whether the model has learned that characteristic of a graph, which yeah, it's kind of still following the traditional pattern you'd have. So you have the training data, which is fed into the model. And from that, we make predictions about the edges in the test set or at the test time. And then we have some evaluation metrics that we can apply to that. But what we have essentially for each characteristic is we specifically have designed the training data and the evaluation metrics so that we can evaluate whether the model has learned that characteristic. This is a list of the different characteristics, and we will go through all of them in turn. And the tests for each of them are quite specific. And so when we're going through the experiments in a moment, we'll go through it as a whole with the experimental setup and the results together so that you're not trying to remember what we told you 8 characteristics ago about the setup. And generally, we kind of group them into 3 areas. So we started with some general graph features, which to some extent maybe aren't even specific to temporal graphs. For instance, the density of the graph. Also within that, we included the temporal granularity, so kind of how the importance of the timestamp that is associated with the edges. Then we also have a few that look at temporal patterns within the data, such as edges which appear with a certain periodicity in the time. And also then some of the kind of classical edge formation mechanisms that have been used to motivate different algorithms that have been developed for creating networks. But before we go into the individual ones, I'll just start with some general kind of setup explanations. And so across the different characteristics, we have a mixture of empirical and synthetic data sets. Where we're using the empirical ones, we're using these 4 different empirical data sets. Enron is emails, Bitcoin Alpha has like kind of financial transactions, Wikipedia is to do with Wikipedia edits. And yeah, so when we're using empirical ones, generally we're running it on all 4 of these, or occasionally only 2 or 3. And then we also have synthetic networks where we've specifically generated networks with a certain characteristic so that we can measure the extent to which that's reproduced or how it affects the predictions made by the model. And for each characteristic, we're only using one or the other of these. Although sometimes the synthetic graph is created by taking some subset or time snapshot from the empirical data sets. And then in terms of training the models, we have run this with 8 different models listed here. I won't read them out, which all kind of happen to be continuous time models, although we weren't actually kind of necessarily restricting ourselves to those types of models, but mainly because we use the implementations from the diglib GitHub repository. And again, because we're not hyper focused on maybe traditional performance measures, and we haven't across the board done lots of hyperparameter tuning, but we have later checked some of the hyperparameter configurations to check that our conclusions aren't changed. That's still being finalized. We do have some initial indications that for the most part nothing changes, but we've used hyperparameter settings that have been found to have good performance on the benchmark datasets without necessarily being the absolute best. And then just to kind of give an idea of the scale of the number of models we've trained, when we're using the empirical datasets, we ran each model with 10 different training seeds. And when it's with the synthetic ones, we generated 5 synthetic datasets and then trained the model with 5 different training seeds, so 25 in all, obviously across the 8 different models and generally across multiple data sets for each characteristic. And now we'll move on to the first characteristic, which we looked at, which was temporal granularity, which is essentially looking at the importance of the granularity within the timestamps associated with the edges. So we have the original data sets, which generally use Unix timestamps. And first of all, we created a discretized version following other work, where, for instance, they're grouped by week instead of having the exact moment. And then we thought, why not even take that further, and we created a flattened version where every single training edge then has time step 0, everything for validation time step 1, and everything for test has time step 2. With all three of these, we make sure the same edges are in those different splits, regardless of which version we're using. And for each of these, we train a model on that data set and then compare the performance on the test set of edges under the procedure that DigLib uses for evaluation. I added this note here. We're looking at both with and without removing duplicates, but the results here will just concern when we have removed the duplicates. So when it's flattened, if the same edge would have appeared twice, it only appears once within that time step. And this table is quite big, but I will pick out a few values on it. So for instance here, if we're just looking at the Enron dataset for corn, we can see that on the left, well, of these three values, the one on the left is the continuous data set, so the original one. And as we go to the far right, then we have the flattened one where basically most of the time information has been removed, and that has considerably degraded the performance, which is something that happens across the board with the different models and the different data sets, for the most part. But here with corn, we can see the discrete version in the middle actually hasn't really degraded the performance very much at all. So removing some of the granularity hasn't really reduced the performance, in contrast to maybe Graph Mixer here, where there is that greater differentiation between the continuous and the discrete versions of the dataset. In terms of the performance on the benchmark metric. And so for this, we have a mixture of some models where we say that they do certainly seem to learn and benefit from the temporal granularity, and others where they seem to somewhat, but not completely, depending on how much of a drop-off in performance there is when we remove it. The second characteristic here is direction, and I'll just start with explaining some of what exactly I will mean in a moment. And so when we're considering direction now, we're kind of considering that there can be an edge and a reverse edge, which is between the same nodes but in the opposite direction. And we also rely heavily on the idea that sometimes we have positive edges that are appearing and negative edges that are not appearing. And for this, we constructed 3 different data sets, one of which, so the one labeled as original here is the same as the discretized one from the last characteristic. But then we have what we call directed, which is where every time there is a positive edge, like on the right-hand side here in this diagram, we have the positive edge in one direction and a negative edge in the opposite direction. When that happens, we make sure that the negative edge in the opposite direction explicitly appears in the negative edges that the model is trained on. Because normally, if you're doing random sampling, it's very, very unlikely that exactly that negative edge would appear in the training. So here we explicitly make sure it does, so that it's really clear that there's a difference in the training between the edges in the 2 directions. And then we have the undirected version where for every time there is an edge in either one of the directions, we also include it as positive in the other direction or as negative. If it's sampled as negative, we would include it in both directions in the training. We do account for the scenario where maybe both edges already appear or don't appear in different things, but if an edge appears in one direction, that's where we then specifically manipulate the training data there. And so again, we train the models on these 3 different data sets, and we compare the differences in probabilities between these pairs of edges in the test data where we know one does appear in the test data and the opposite direction doesn't appear. And so here in the results, this is the first graph we get from just using the normal data. And we can see that slightly model dependent, but roughly around 50% of all edges are predicted with a difference of less than 0.02, because we have the cumulative fraction on the y-axis, where we'd say they're more or less predicted with no difference between the 2 edges when we look at the pairs. And when we instead switch to here in the middle with the really explicitly including the negative reverse as a negative training example, This reduces to about 30% of the pairs having more or less no difference. In contrast, when we include them in both directions, we can see that the line moves in the opposite direction. So we start to decrease the difference between the pairs. But overall, with these changes, there's always still a large proportion that is treated the same when we would expect it not to be, or treated differently the other way around. And so we conclude that the models have a limited ability to learn direction based on these results. And the third characteristic that I'll be explaining before Tobias takes over is density. And so when we're using these benchmarks and carrying out testing, we make predictions for all of the positive test set of edges and also generally the same number of negative examples. But obviously, if we're wanting to look at density, that's not going to be particularly helpful. And so for this characteristic, we made predictions for every single possible edge in the network, which is slightly computationally expensive, but it means that we can then look at what density of network is predicted afterwards. And within that, we also varied the proportions that the model is seeing in training. So normally, as well as in testing, having this equal split, in training, often you also have an equal split between positive and negative training edges. And so here we started with that, but then incrementally doubled the number of negative examples so that it was seeing, so we trained models with seeing ever smaller proportions of positive edges, which we would expect to kind of reduce the density predicted, but we wanted to see how this interacted with what the model was predicting. And obviously, if we have predictions for all the edges, we can calculate the predicted density overall. And so what we have here is as you go kind of from right to left, we have an ever smaller proportion of positive edges because we've increased the number of negative examples. So on the left-hand side, you've got 1/33 of the edges being positive, and on the right-hand side, half of them with the more like normal setup. And we've also added two lines on there. The line on the like the horizontal line towards the bottom is the true density of these networks, which is very, very low. And then the dotted line that slopes down is showing what kind of the density would be if the only edges that exist are the ones that are appearing in training. So 50% on the right-hand side and reducing down. And I mean, from the graph, we can see none of them are ever getting the true density, which, I mean, is perhaps not that surprising given that in training, they're not seeing the true density represented to them. But certainly with current training procedures, the models are not able to learn the true density of these networks. And now I'll pass to Tobias to present the second half. Are you going to share your slides as well separately?
Yeah, I'll be doing that. Okay, let's check. You can see this. Okay,
Yeah.
perfect. Okay, yeah. Thanks, Abby. Also, yeah, once again, hello from my side, and really thank you very much for having us on short notice. It's like, yeah, really great to be able to present here. So, yeah, I guess I'll continue. So basically, Abby now closed with what we had introduced as, I think, general graph characteristics, and now we go to the more temporal oriented graph pattern. So, though, well, with what we have next, I guess there's probably not so much going on. So the next characteristic that we have is persistence. And what does persistence in our context mean? It's basically we have this graph at one time step, and at the next time step, the same graph, and at the next time step, the same graph, and forever the same graph. So basically, we have like the probably easiest pattern is just, well, whether a model can detect a network which is just like the same over all time steps. And obviously in real life, we will not probably not like test on something like that, but still we'll often see that like there's, well, maybe not the full graph, but subnetwork with similar patterns which are which are like, yeah, almost constant in some cases. So yeah, what we do is we basically train models on identical snapshots and times, and models should learn to predict exactly these edges. Now, how we like generate the graphs, we basically took some of the empirical graphs and just like sample snapshots from there, from these, and these were just replicated. So you know how these things come into being because they're all associated with some data set also in the paper. And what we see here is basically results on the UCI, or like snapshots from the UCI data set. Now, what do we see here? I hope it will be easy to understand. But basically, so the y-axis is average probability score. Is like the probability that the model assigns to the edges, whether they exist or not. So we basically tested on all edges that could be. And in green, we have then for each of the 5 times 5 models, like 5 seeds times five data sets, 5 times training seeds. Yeah, the average probabilities over all positive edges in green and all over all negative edges in red. So basically, what we would well expect to see is that, well, obviously this should the green and the red should be like very far apart from each other because, I mean, yeah, this is like the easiest thing that you could probably get. And if you see to the left, we have like corn and Dickformer, which do this like very well. So as one would hope to have, yeah, the positive edges are always like predicted to be positive with very high confidence, and for the negative, this is the same thing. And we also say that TJET or TJT, I'm not even sure how we could, or TGAT, whatever you want to pronounce it. We also would say that there's like reasonable confidence at least in there, so that these are like separated to a reasonable degree. Um, However, we also have like methods such as Graph Mixer and TCL, where we see that, well, they seem to be like separate between the point clouds, so to say. So there's like different, but it's also like, well, something which we intuitively would have thought is like much less confident than one maybe would have expected. And then there's also like a couple of models where oftentimes the predictions are not even like separate. So for Dyrel, for instance, or for Jody, these models seem to struggle to quite a surprising degree in separating these different kinds of edges. So so there we were like quite surprised to find that, and this is something where we think, well, interesting, but apparently that seems to be hard for these models. And yeah, so this was persistence, and the next property is more or less, or characteristic more precisely, is quite related to that. We're taking it now one step further. So before we basically had the same snapshot every time, and now, well, we start with one snapshot, we go for another snapshot, and then we repeat the one that was first, and then we repeat the one that was second, and so on. So basically, we have like a periodic pattern. We're basically like switching around the network that we see in but basically in a fixed periodic order. So for this case, which we'll show, basically every other time step will be like the same as the one that was like 2 snapshots before. And training regime is basically simple, then basically the same. We train on that, and then well, models should be distinguished between 3 kinds of edges. So the procedure was the same pretty much as before. We basically sampled snapshots from the empirical data sets. And we did this in a way such that there was always some kind of overlap between the distinct snapshots, so that we would have edges which always appear in both snapshots, edges which appear at specific periods, so only like at odd or even time steps, in the case of like 2 time steps, and edges which also never appear. So these would be like different cases, and these we then distinguished in our analysis. And again, we have like similar plots where we plot the average probabilities per edge group per model. Now here we have this again, like for 2 time steps. So basically, we predict then also on 2 time steps. We see for every model that we have like grouped these. Left would be the prediction on the odd time step, right would be the prediction on the even time step. And the edge group then is basically similar to what we tried to explain before. So basically, the green dots correspond to edges which are always there. So this is something which is always a positive edge. So these edges are always present, and Yeah, and conversely, the red ones, also like in the previous characteristic, these are always negative. And then we have odd and even. So basically, the blue edges only appear at even timestamps, so to say, and the yellow ones only at yeah, at the odd timestamps. So basically, ideally, we would see something like for, in this case, Graph Mixer, where yeah, the edges which are always there have high confidence, and then also at the odd timestamp, the odd edges have high confidence, and at the even timestamps, the even edges have high confidence. And if you look closely, somehow only Graph Mixer and TCL appear to properly reproduce this training pattern in our experiments. So yeah, there for this what we really see on the left. If you look at the upper half, just like really to recap, I'm not sure whether I'm interpreting your faces probably, but it's basically like yeah, we see yeah, at the odd time step we are highly confident for the odd edges to appear, and the other ones have low confidence or like low probabilities, and so this is basically what we would want. Then if you look into some other models such as TGN, TGAT, or DIREP, they seem to struggle to different degrees. So DIREP doesn't, I mean the edges which appear at all time steps, they are like most it still is most confident about, but it doesn't seem to distinguish between the other two time steps too much. And also for TGAT and TGN, it's basically we get like high confidences also for yeah, for edges which do not appear at this point. So we would argue that these models struggle. And what's also very interesting is what Korn and Dickformer do. They behave what I would probably call like a similar to edge bank. Basically, if an edge appears oftenly, it will get high confidence and it doesn't really seem to consider the timestamp. So this was also something which was quite surprising that it's basically just yeah, evaluating also like seeing, okay, these edges appear often and thus they get high probability, but the timestamp in there is somehow not considered. So that was quite interesting, at least in our opinion. Okay, we continue to the next graph characteristic that we test, which is called recency. So the intuition, and maybe this is also motivated in part on what we refer to like with with like this paper where I think Cornell et al. Used heuristics like more recent edges to predict them with higher likelihood, and based on this heuristic, you could like do well in many benchmarks, and one might also expect that temporal graph learning models would favor more recently observed edges in their predictions. And how do we test that? So we basically created multiple graphs, or like we construct a temporal network, and we did it in a way that distinct sets of edges appear at every time step. So let's say we start with just such an example graph here, and at the next time steps, I mean, we always keep the same nodes, but at the next time step, there's basically a completely different set of edges. And for the next time step, there's another very different set of edges. So basically, we have complete disjoint sets of edges for every time step, such that, and then when we train a model on this network, the idea is basically that the only information what it really learns is like when an edge was seen for the last time. We also made it again, it's like completely disjoint edge sets, so every edge that occurs will only occur once over the whole thing, but obviously there were also some edges which never appeared for training. And yeah, we did this also like for many time steps and also like in a similar fashion to what we have before. We basically did this from taking some of the empirical data sets, taking some snapshot from there, and then we basically considered only the nodes which were at the specific time step at this time point and the edges there. We just considered the density, but then based on this density which we observed, we basically then yeah, we sampled these networks so that we have this setting. And now that we have created these networks, we trained the models, and we basically compared the predicted edge probabilities based on at which point in time the edges were seen the last. And yeah, here's now the results. As before, okay, so it'll cut off, but the y-axis are different, are again like the edge probabilities, like that were assigned to the models. And note that in part we have different scales here. So for instance, on the very left one, on the N1 dataset, it's just like a very, very small window where the probabilities actually lie. And now the x-axis is like the time step that an edge has been seen for the last time. So time step 0 basically means this is the predicted probability for edges which have been seen at time step 0, and at 9 is obviously then yeah, the predicted probability for edges which have been seen most recently at yeah, training time 9. And what we see is, well, basically we don't see much. So there doesn't seem to be like a real connection or like big connection or like a consistent trend. And somehow, yeah, we deduce that there doesn't seem to be like much, like the models don't appear to make much from, yeah, how recently some of the time steps have been seen, which we also find somewhat surprising. But yeah, maybe that's something which yeah, can be like considered in also like, yeah, further model design. Okay, this were the temporal parts, and now we went to like the edge formation characteristics, which would be like the final two properties, and the first of these two would be homophily. And so basically, I mean, what does homophily mean? To begin with, homophily basically means that, well, similar edges should be like more likely to connect with each other than, well, different edges. In that part, in this characteristic on our setup, we basically trained that using, or tested that using stochastic block models. And stochastic block models, I mean, what we've seen here on this slide is something which you could, well, interpret as like the heat map of some kind of adjacency matrix. So assume this is like an adjacency matrix of like a big network. They are arranged in a block that there's basically two groups. And then the probability of having links within the group is much higher than the probability of having links between groups. This would be like the homophilic regime. So in our setting, we basically had this homophilic model where we have like in-group probabilities of an edge of 0.005. And for between groups, it's basically 5 times lower. So we have still some connections going on, but it's like, yeah, much higher within the groups. And we basically just simulated some temporal aspect there by yeah, reproducing or like rerunning reproducing these stochastic block model for 100 timestamps and feeding that into a model. And I mean, this is now an illustration of a homophilic variant, but we also considered a heterophilic variant where basically the probabilities are just switched around so that intra-group links are much less likely than links between the groups. So we would also test both scenarios. And now intuitively, models should be able to distinguish different edge types. And ideally, the predicted edge probabilities, which we'll also see in the next slide on the big table, they should also ideally be somewhat proportional to the well model probabilities. So obviously that would be like hard to achieve, but yeah. Now here comes the results, and yeah, I guess it's now a big table, so I'll try. I hope that we can like kind of like steer this around. So basically, we have like the left half for the homophilic model and the right-hand side for the heterophilic model. And now maybe let's just start with the average edge probability. So this is basically, yeah, really, yeah, just the average probability that the models assign for the distinct edge groups. So 0, 0, and 1, 1, like 0 and 1 are the different groups. So 0 to 0 and 1 to 1 would basically be the probability for an edge within groups, within these individual groups, and 0, 1 would be like probabilities for the edges between groups. And now just as an illustration for corn, which have been marked. So for the homophilic, network, we basically see that, yeah, the within group links have much higher probability than the between group links. So only like 50% higher, but still noticeable. And for the heterophilic stochastic block model, we see like the opposite pattern. So one could argue that this model and also most models, if you look down, this will look the same for most models. They can indeed distinguish the groups. Now, if you actually look at the fraction of predicted edges, so this is basically we predict an edge to exist if its probability is bigger than 50%. Well, it seems it gets like very binary, so to say. We also looked at these, actually also looked into like ranked to like the rankings of those most likely links, and it looks quite similar. So basically, like, yeah, they really tend to favor now, yeah, whatever group kind of connection is like much more likely. So yeah, generally we find that models distinguish intergroup links and intergroup links. But this does not hold for all models. So if you look at Jody and TGN, there we see some weirder patterns, such as for TGN, they're just like always kind of low, and or Jody somehow just not liking not liking specific yeah not sorry somehow Jody favoring 0 to 0 links in the heterophilic regime to some degree, which may be unexpected. So some of these models did not do well, and somehow they did not really distinguish these different kinds of link groups. And what was also like some kind of positive outlier to some degree was DIREP, which somehow did not converge to fully binary deterministic predictions. But there we actually have this case where also we have some well, some predict some positives for the less likely edges in there, even though nothing, I mean, it's not like entirely proportional in any case for the model probabilities, which were all like 5 times more or less. But at least, yeah, we have for direct something which is not as, so to say, binary. And finally, we have preferential attachment, where the first time step is a Barabasi-Albert model. So basically, like, so I should maybe start with what we encode. So basically, preferential attachment means that nodes of high degree should also be more likely to receive additional links. And if you like want to generate a graph with that, the Barabasi model, which is illustrated in here, is like a classic. So basically, if an edge is highly popular, it also has a higher likelihood of receiving future links. And basically, we also like produce a temporal variant of that model by initializing with such a model, and then also adding like links in future time steps based on yeah the node degrees of adjacent nodes. And if we want to like check whether models learn preferential attachment, we basically evaluate the predicted probability of unseen edges based on the degree of adjacent nodes. So we basically test whether like yeah high degree nodes are indeed more likely to receive a link. And we also like measure likelihood again in like the predicted edge probabilities, which we also aggregated. And the results this time, I mean, I remember like producing the plot after everything has finally been computed, and this was actually something where I thought, finally a nice result. So this is more or less as you would expect. So on the y-axis again, we have like the average probabilities. So I think this should be like familiar by now. And on the y-axis, we have like the degrees of it, like degrees of adjacent nodes, or like average degrees of like a adjacent node is basically ordered by a node for by like node class, and for there we average the probabilities. And what we see is that indeed with exponentially higher node training degrees, also the well probabilities actually rise, and this is like kind of like a nice curve. So this is kind of like what one would expect to have, or like one would kind of hope to have. And yeah, to me it was even like to some degree reminiscent of the power law degree distribution of the Barabasi-Albert model, and we conclude that all models learn preferential attachment. Okay, so this was a final property, and the next slide is then kind of like a summary where we have like distinguished between yeah, green for learns it, yellow is learns to like limited degree, and red is probably doesn't learn this characteristic. Okay, so maybe just like yeah, not do a quick recap and like discuss what contributions and limitations are. So what we kind of did was more or less propose what well one could maybe call, hopefully call, a novel framework for well maybe something like interpretability driven evaluations of temporal graph learning models. So we hope that at least you understood what all of the characteristics were about, and hope that this might kind of like yeah help at illuminating some of the results, which also might come out of well other benchmarks or something like that. And what we found were like some limitations, which at least I, for my part, found also quite surprising in state-of-the-art temporal graph learning models. But also want to note like these are like 8 characteristics, and they may be relevant in some applications, but maybe there's also cases where I don't know something like recency might not even be relevant for your applications. So it's not like we argue that a model must adhere to all of these, must be able to learn all of these 8 characteristics. Also, we do not say that this is like fully extensive that is like everything. So there could also still be other things of interest. And but still, we would argue that maybe awareness of these properties, yeah, of these yeah, learning patterns might inform future usage of network models. And as for limitations, so first of all, like, yeah, we have a limited selection of data sets, but obviously we also have to meet a lot of constraints. We didn't yet drop the number, but at this point we already trained like, I think close to 7,000 or even more models. So it's getting a lot if we train everything. And also to be able to like train these models, the data sets cannot be too large. And ideally they have like Unix timestamps, which can then be discretized to do everything. So it's also not that easy to like, yeah, actually find a lot of things which are like suitable. Also, it's a purely an experimental study. Theoretical analysis is out of scope. I mean, I can say that also, obviously, I was interested, or like we were interested in getting to the bottom of why some certain things are. But then if you look into the models, yeah, for instance, for Graph Mixer, it has like some distinct fixed, just as an example, Graph Mixer has like some fixed encoding for time, which is, yeah, where we say, okay, this is somewhat different in that it's like fixed and not with learnable weights. Maybe that helped. Would be an intuitive thing to look at, but there could also be other aspects, and I think it would require much more principled studies to actually look into that. Also, we focus on isolated characteristics. Maybe some people would also be interested in combinations, though I think that we did this deliberately, so we could actually like pinpoint two specific things because when these combinations could also be hard to figure out whether, I don't know, something is more to preferential attachment or more to homophily or something like that. And yeah, we have maybe limited hyperparameter settings, although we did a lot of ablations, but obviously we cannot cover everything, and obviously we cannot rule out that we have exhaustively looked into all of the hyperparameters, even if we like finish all of the things which we are still running. And yeah, and only continuous models were considered, so maybe future work we could also, or somebody else could also look into discrete models and how they behave there. Okay, and if you want to look at the preprint, here's a link. I think it's also on your webpage. And oh damn, we are quite over time. So sorry for that. I hope there's still room for questions. We're for sure happy to answer many questions. And again, sorry for like taking longer than that. Yeah, again, it was quite short notice, but still, yeah, just noticed.
Yeah,
So thanks again
yeah,
for having us. And yeah.
yeah. Thanks for the presentation and the interesting project. We are actually not over time. The reading group is
Oh,
scheduled to be 1 hour. So
I thought it should be half an
one
hour presentation or
hour,
something like that.
yeah,
Okay,
one
then.
hour Q&A. I think we're okay, right?
Yeah, yeah.
Um, and yeah, I'm just curious. So part of this work, and we did a similar work as well. That will be presenting at KDD 2026. But basically, we had a similar idea where we try to understand the limitations of current models, as it's not very transparent from kind of real world data sets. Kind of part of the motivation of your work as well, right? But I think one thing that's not clear is basically how to connect these empirical results with the actual things that the model learns. And I think there's a lot more subtle details there as well, because I think the current models, because they are trained on a single data set, potentially, depending on the hyperparameter that you use, it's either overfitting or underfitting, depending on the number of epochs, the number of layers, the receptive field. So there's more going into just just the architecture itself, but also just generally the hyperparameter choice. And we have the same issue of basically if you want to test everything, that will basically means like infinite runs, right? So train these models like infinite times and try to understand the whole broad picture. But I'm trying to get at is that what do you think about some? So you mentioned that this is out of scope, but from the findings here, do you observe some patterns from these architectures? Is there some general rule of thumb that you can draw from these? So like one idea that come to my mind was that we know that TGAT is a subset of TGN. So TGN is basically TGAT plus memory. So one thing that's surprising is that, for example, once you add the memory, now TGN can understand better for temporal granularity, but based on the table, the homophily aspect is lost, right? So I think there's a few of these subtle things that we can understand from the architecture point of view. So I'm not sure what's your take on this, and then what's your findings throughout the project.
Yeah, I mean, this is like something which, this is like a very good point, and oftentimes it's also like a question of, I don't know, what a model should in theory be able to do. I mean, it's the same thing with like all of those transformer models, which also should in theory be able to like learn temporal patterns or like having seen something like that. And yeah, it's also I like I cannot ha I don't have like an explanation on why somehow the memory adding the memory kind of like does harm this, or maybe or if it's if it's like specifically the memory part, or if it's like the maybe like even something else which is maybe a little bit overlooked. So it's frankly it's like hard to like, yeah, as you said, it's really hard to pinpoint these things. And I feel like, as also said before with like this graph mixer example, or I don't know, I've also like considered other examples of, I don't know, I think Dirac had something like some very stochastic inner matrix, which might also explain like why it's more likely to go for well, non these non binary predictions or something like that. But I feel like it would be like a lot of guessing, and I feel like it would actually like require some more principled experiments to actually see like, well, try this with or without, and also like, yeah, maybe I think it would probably require like some more specific experiments where we just compare these two models and also try to rule out all other noise which would kind of come in there. So I would rather argue that maybe like with like other benchmarks and also our benchmark like altogether, we could probably like look into more specifically into these differences. But I don't know. I feel like I don't want to like make a strong statement or like guess something where I mean, I think basically like, yeah, what we have is like something which could give pointers, but I feel like making strong conclusions is something which might be a little bit out of place, so to say. So I'm not sure whether it's like a good answer, but I also feel like maybe I'm not the one at this point. We should probably not make like strong conclusions.
Hmm. Hmm. Yeah. Uh, yeah, makes sense. I'm more just asking for like high-level intuition and then where you see this goes next. And also another thing based on my experience is that so we recently have the TGM library release, which basically have most of these models, like some of them, and is much faster than DigiLib. But the main thing that we find out is that the performance numbers of the model is actually changing as well. So sometimes for DigiLib, they also have a lot of these hard-coded little
Mm,
things where they hard code in the data loading and this kind of stuff, as you're probably aware, right? And it's very easy to make errors in terms of running these models. And sometimes we find divergent numbers. So for example, TGAT is much better performing on the TGM implementation than the digilib one. And it's not clear, what exactly is causing that directly, but I think potentially just trying different runs, like across different implementations, could be from the original implementation as well. That might change things a little bit as well. Um, so just to kind of bring that to raise that point as well. So we tend to overfit to digilib implementation because
mm,
this has the most models, seem to be the easiest one. But from our benchmarking, it's actually the least efficient. Usually has the most bugs because many things are hard coded, and you have a lot of like if-else statement about if you are this model, then do this
mm,
and this kind of things, right? So, as you're probably aware, so yeah. But yeah, just potentially there might kind of bring some conflict into these results as well, with potential like implementation difference as well. So it's very hard to kind of pinpoint exactly where this at. For your future work, do you have some ideas on what you want to do like after wrapping up this empirical study?
um, I mean, what I would personally find interesting actually is like this final limitation where we only like had well, we only considered continuous models, and I actually wonder whether like some discrete time model would also have like some kind of very different behavior on some of the properties. Like, I don't know, I feel like maybe the discrete models where you in part also like work with, I don't know, feeding something like whole adjacency matrices in there. Maybe they have some better notion of density or something like that. So I feel like this might be something which would be interesting to just maybe like find out something which is like conceptually different, but which could be interesting. Um, and then yeah, other avenues could go also like as you indicated, maybe like looking into some of the specific model differences in what models learn and investigate these things. So for me personally, I mean, I'm personally just finishing up my PhD, so this is obviously like my most imminent future work that I will have to do, and this is like the biggest thing on my list. But yeah, there's also yeah, these are the things which I would be interested in. And
Yeah.
yeah, maybe Abby will also have like some other ideas on where she would go when I'm not around in Mannheim anymore.
Yeah, I don't know. I guess for me, like an open question is also the fact that for some of these characteristics, we've kind of said none of the models are learning this, but maybe there would have been room there to try and construct different measures to measure the same thing and see if maybe it's just the perspective on that characteristic that is the issue there. Whether it'll make any difference, like I mean, I think the only one we said isn't learned at all is recency, which again is not something where maybe we even care if the models learn it. But I think certainly we've seen as we've kind of derived different tests and as we change them somewhat, that sometimes the combination of them could give interesting insights as well.
When I was looking at this table and thinking about future work, I thought it would also potentially be super interesting if like a user who has a data set where they want to predict something and they don't really know what model to use. Something like this could be super helpful for model selection. Like you check your data set, what kind of properties does the data set have? Is periodicity important? Is recency important? And then based on those like similarities to the different categories, select a model or maybe automatically check for similarities with your categories and automatically select a model. Was this something you were thinking of or plan to look into?
I think it was certainly something we talked about in that, like from this, we can certainly see the difference in model behavior that means that maybe sometimes one is more desirable than the other, as you said, in kind of the context of the data that you're working with, or even the kind of concept you're trying to make the predictions for. Maybe you're more interested in certain aspects than others. I don't know that we have any plans to look into it specifically, but I think certainly, I mean, generally, I think the concept that you want to choose the right model for your specific task is certainly important.
Yeah, makes sense.
Yep, sounds good. Yeah, thanks for the presentation. If there's no other questions, we can also wrap up here. Yeah, let's thank the speakers for presenting their recent work and looking forward to seeing new version of this paper as well.
Thank you
Thanks.
very much.
Yeah, thank you very much. Once again,
Thank
thanks
you.
for having us.
And best of luck with your PhD thesis
Thank
writing
you.
and everything. Yeah.
Thank you. Thank you.
Bye.
Thank you. Bye.
Bye.